Welcome to this online course about the exploratory data analysis in Python, organized by your data teacher. First of all, let me introduce myself. My name is Gianluca Malato. I am 34 years old and I live in Italy. I have a master's degree in theoretical physics of disordered systems and I am a data scientist. I write articles about data science on Towards Data Science online publication, and of course I teach data science on my website yourdatateacher.com. The purpose of this course is to study the exploratory data analysis. The exploratory data analysis will be introduced in the next video, but the student who attends this course at the end will learn how to start analyzing a dataset of a machine learning project, because exploratory data analysis is a particular step of a machine learning project. It's the first step after the dataset has been built. Everything starts from analyzing the dataset we are going to work with before giving this dataset to an algorithm or a model. Then the student will learn the basic univariate and multivariate analysis, that is the core of the exploratory data analysis, and we are going to see some of the most common Python libraries. Every content of the course is explained using a practical example in Python. We are going to use Python for all the examples I'm going to show you and for all the topics we are going to cover. Python is a very powerful programming language for this kind of task, and it has almost become an industry standard when it comes to talking about machine learning, and it is the tool we are going to use in this course for all the topics we are going to cover. In the next videos we are going to see the practical examples in Python with several techniques of exploratory data analysis, and in the next video we are going to see what exploratory data analysis actually is. Let's talk about the topic of this course, that is the exploratory data analysis. Exploratory data analysis is the first approach to a dataset before applying any model in machine learning. We are talking about exploratory data analysis both for supervised machine learning and for unsupervised machine learning. The idea of exploratory data analysis is that before applying any algorithm or any model, we can use this technique, this set of techniques, to understand, for example, the shape of our data. For shape, I talk about, for example, some high-level statistics, the mean, the variance, and so on. This is often referred to the univariate analysis of our dataset. So we take each variable and we analyze it independently. Then we have the multivariate analysis, in which we understand how the variables interact with each other. Again, this is not related to a particular model we are going to use. This is related to the dataset itself. Then, if we have a supervised machine learning model to build, we can see the predictive power of the variables. So if we measure the correlation between the features and the variables, we can calculate the predictive power of each variable. And this is very useful because it gives us a first idea of the information we are going to feed our model with. Then we can use the exploratory data analysis to detect the less useful variables, for example. There are several situations in which the variables are not useful. For example, they have a low variance, they have too many missings, they are not so correlated with the target variable, and so on. Then we can use the exploratory data analysis to extract some information from our dataset before applying any algorithm. The idea is that exploratory data analysis works before any algorithm. We take a look at our dataset just as it is. We don't transform it. We just extract as much information as possible without applying any particular algorithm. Exploratory data analysis often uses data visualization to extract information from a dataset, because data visualization is a very powerful approach for extracting information that is hidden inside the data. So the idea of exploratory data analysis is to analyze our data and try to understand the information, to extract the information from our dataset before applying any model. In this way, we understand something more from our dataset, and we can then choose the proper transformations to apply to our dataset, and we may be able to select a possible set of models, because if we know how data is shaped and how the variables interact with each other, and possibly with a target variable of a supervised machine learning problem, we can make an idea of the model that is more suitable for our dataset. This is the main idea of exploratory data analysis. Extract information from data before applying any algorithm. The output of the exploratory data analysis can be a project deliverable by itself, and according to my experience is very useful even for non-technical people, because exploratory data analysis makes use of data visualization, which helps several people understanding the information behind the data without applying algorithm or models. This is the topic of this course. We are going to see all these topics here for extracting information and understanding our data better. The main tool we are going to use in this course is Jupyter Notebook. Jupyter Notebook is a particular integrated development environment, very useful for data science, because it allows you to create interactive dashboards or mix code, documentation and charts all together. So you don't need to write all the code in advance and then run it. You can run the code while you write it. To install Jupyter Notebook, you must open a terminal of MS-DOS or a Linux terminal and type pip install notebook. Then you can type enter, and once the installation is completed, you can write Jupyter Notebook. Typing enter, a new browser window will open and its appearance will be like this. This is the folder I've created for this example. You are going to see all the folders of your computer here, and you can, for example, create a new folder using new, or you can create a new file that is Python 3 file. So if you want to create a new object where we can write our code in, that is called notebook, we can select new and select Python 3. A new window opens and we can start using this object that is our notebook. A notebook is made by a name. For example, we can change the title of this notebook to test notebook. And we have a menu bar when we have many options, and this is the main part of the notebook, that is the first cell. Each notebook is made by cells. Each cell is made by some lines of code that are executed together. For example, we can print hello world, and if we want to execute this cell, we can, for example, click on run, or for example we can type control and enter, and this is the result. The cell is executed and the output is printed next to the code. We can now create a new cell using, for example, the plus button and write another code, for example print hi. And if we want to execute this code, we can still type control and enter, or we can type shift and enter. In this case, typing shift and enter, the code is executed, the output of the cell is printed, and a new cell has been created. Using the cells in a notebook is very powerful because we can run previous cells as many times as we want. For example, we can run this cell again, we can run this cell again. I'm using Control and Enter to run a cell. Or for example, we can define a variable in a cell and use it in another cell. For example, I can define a variable here, a equals 4, Shift and Enter executes the cell and creates a new cell, and then I can type print a. And this is the result 4. But for example, I might want to change this number to 400. I can execute this cell and move to the next cell using Shift and Enter. Then I can execute this cell using Control and Enter, and this is the result 400. So in this way, we don't need to type all the code in advance and then execute it like, for example, when we use PyCharm or other integrated development environment. This is an interactive tool. We can execute the code while we are typing it. And it's very useful when you have to analyze some data, because when you have to perform some analysis, you don't know in advance the code you are going to write. So you start analyzing your data in some way, then you go on following the way the data suggests you. So an interactive playground is very useful when you have to perform data science tasks or data analysis tasks. And it's much better to use such tools than traditional environments. Another very useful feature of Jupyter notebooks is the possibility to use Markdown code. We can put our cursor in a cell, go to this drop-down menu and select Markdown. Then this cell will contain Markdown code, for example, a title. And as you can see, this cell has been formatted according to the Markdown code I've written. The next cell is a code cell, and a code cell is a cell that contains code written in this programming language over here, that is Python 3. So we can mix text and documentation. For example, I may write test. Step 1, define a variable. Step 2, print a variable. As you can see, we have a list here. Then we can type our code, a equals 5, and print a. And this is the result. So this is the environment we are going to work with. It's very used in data science. There are many implementations of this tool. Jupyter by itself can be used as a standalone object, but it can be used, for example, even with R code. And there are other implementations because it's open source, so some companies, some people created their own version of notebooks. So a notebook is essentially a document where you have code, the result of this code, and text, formatted, for example, in a Markdown way. We are going to see in the next lessons that this object can contain even charts. So Jupyter Notebook is the tool we are going to use in our course for all our lessons and examples. Some options of Jupyter Notebooks are, for example, the possibility to run all the notebook in a single operation. You must go to Cell and then type and then select Run All. This will run all the notebook. Another option, and it's very useful to apply, is to export this notebook, for example, in HTML format. You can go to File, then Download As, and you have many options. You can download it in Markdown, PDF using LaTeX, Python, HTML, and so on. You can make a copy of this notebook, for example, if you want to duplicate it and modify it later. Notebooks are automatically saved after some seconds, And from the file menu you can create a new notebook that will be created in the same folder of the actual notebook. If we go back to the folder we have created this notebook in, we see that we have a new file that is our test notebook, and the test notebook, if you remember, is the title of the notebook, and this file has this extension IPyYNB. This is the extension of the Python notebook using Jupyter. So notebook is essentially a file with this extension. This way you can create your notebooks, you can navigate through your folders, selecting your notebooks, working with them, and you can, for example, share your notebooks because they are simply these kind of files. The first thing we have to do when we have to work with a dataset is to take a look at this dataset. Before calculating anything, we have to see our data, our raw data. So in this lesson, we are going to see several methods to take a look at our dataset. First of all, let's import pandas. Then let's import our dataset. We can store this dataset inside a data frame called df, for example. We can use the read CSV method of pandas. The dataset is sample dataset in this example. Now, the first thing to do is to take a look at this dataset. How can we do this? Using the head method that gives us the first rows of our dataset. So df.head. These are the first 5 rows of our dataset. We can understand several things with this first site. First of all, we have some missings here. These are situations in which the data is not present. Now we see that we have 31 columns. This is just a sample of the first 5 rows. And these columns are almost all numerical. We can scroll towards the right part of the screen. We see that some columns have not been showed because when the number of columns is high, Jupyter will not show all of them. So maybe there is some information in these hidden columns here, but we are going to see this information soon. And we have a target variable here. In this case is 0, but we can say that the great part of this sample dataset is made by numerical columns. So we have numerical columns, 31 columns, and we have some missings to deal with. And we can see that the order of magnitude of each column is different. For example, we see here that MirRadius has this order of magnitude around 10, 20. Here we have numbers that are lower than 1. As well, this column here has numbers that are lower than 1. So we have different orders of magnitude according to this small sample we have created. We can create a larger sample writing df.head, and the argument of the head method can be the number of rows we want to show. In this case, 20 rows will give us a larger result. As you can see, 20 rows for 31 columns. We still have some missings that we must deal with. A very useful approach when we want to take a look at our dataset is to take a look at the data types of the columns. This can be done using df.dtypes. In this way we see all the column names and the type. As we can see, we have all float64 that are numerical data types. We have an integer data type that is the target variable, and now we have a new column that we haven't seen before, that is the area error, that is an object. Object columns are usually strings or something that cannot be converted into a number directly. We can take a look at this column explicitly writing df area error. So it is a letter, and as we can see, it still has some not numbers. So we have to deal with this column and its missings too. If we would like to see the distinct values of this column, we can write unique. And these are the unique values. So we can see A, B, C, and not a number. So this is a first sight we can give to our dataset, but we can extract more information than this. For example, the number of missings for each column. We can write df.info. We have the name of each column, the type we have seen before, and the number of not null values. So MeRadius has 482 not null records, and so on. So missings, I repeat again, must be handled properly, and the first thing we have to do when we look at a dataset is to understand how clean this dataset is. We say that this dataset must be cleaned when this dataset has some missings. We have to know how many missings we have. Each column has its own missings, and these are the number of records that are not missings with this column here, and so on. So this gives us a quick overview of the number of records that are filled with values for each column. But how many records does our dataset contain? We can use the shape method, df.shape. With the shape we see that we have 569 rows for 31 columns. So using the types, we get the types of the columns. Using info, we get the types and the number of records that contain values for each column. And using shape, we get the total number of records and the total number of columns. Now, another very interesting visualization of the missings of our dataset can be done using, for example, a plot. We can write, for example, df.isNA. This gives us a data frame with the same columns, and true if the cell does not contain a value, and false if it contains a value. We can write sum, and we get this series here in which each record contains the number of missings of that column. If we want a percentage, we just have to divide by the number of the records, that is df.shape 0. And these are the percentages. So this column here has 15% of missings. This column here has 29% of missings, and so on. We might want to know, for example, which column has the highest percentage of missings. We can easily sort this series in this way. And we see that the target column is the column that has the lowest percentage of missings, and it actually has no missings. And the concavity error column is the column with the highest percentage of missings, that is 33. It is very useful to visualize this dataset, plotting, for example, a bar chart. We can use plot kind bar, and this is the result. So this is a very quick overview to our dataset. Let's summarize what we have seen so far. We have loaded our dataset. We have seen the first 5 rows of our dataset, and we have figured out that we have almost all numerical variables. We have seen 20 records of the first records of our dataset, and these are the types of the columns. We have seen that there is an object column. So let's go deeper inside this column here. We see that this column contains some missings and we have letters. About the missings, we can count the missing values on each column. Particularly using the info method, we count the not null values of each column here. The complete shape of our data frame is 569 rows and 31 columns. If we want to focus on the missings, we can calculate the percentage of missings for each column here, using, for example, this syntax. We can sort this series here from the lowest percentage to the highest percentage using sort values. And now we can visualize the missings using a simple bar plot. This is very useful when we have a low number of features, a low number of columns. When the number of columns is pretty high, this bar plot must be created properly. Maybe, for example, we can plot the first 10 columns, the other 10 columns, and so on, or we can make a larger plot in order to contain all the columns. So the first sight we give to a dataset is taking a brief look at its data and taking a look at the type of the data. Finally, take a look at the missings. For example, calculating the percentage of missings for each column, and it is very important when we perform an exploratory data analysis, we can draw a chart, this kind of chart here, that explains how clean our dataset is. Let's now see another technique that is very useful when we want to explore our data, that is called summarization. Let's first import pandas, and then let's import our dataset. Summarization is made this way. It is a method that gives us some quick metrics we can calculate over the dataset, feature by feature. We have, for example, the mean value of each feature, the standard deviation, the percentiles, the maximum and minimum values, and so on. So summarization gives us a brief summary of each feature, giving us the basic statistics properties of this feature. We can summarize our dataset using the describe method. So df.describe gives us this dataset here. For each column, we have the number of records that have values, so that are not missing, the mean value of the column, the standard deviation, the minimum value, the 25th percentile, the median of the column, the 75th percentile, and the maximum value. And this is true for each column. Obviously, it is true for each numerical column, because we can calculate the mean, standard deviation, and so on only for numerical columns. If we go back to our dataset, we see that we have 31 columns, but this summarization has been made only for 30 columns, because if we remember, this dataset has one categorical column. So we can calculate these metrics here for the categorical column, but this gives us an idea of the columns of this dataset. For example, we see that the mean value of these 3 or 4 columns here is greater than the mean value of these columns here. Again, we have several different orders of magnitude in this dataset, and this is a problem we have to deal with, because some models in supervised and unsupervised machine learning don't want to work with columns that have different orders of magnitude. We have standard deviations that are very different with each other, and we have these properties here. This feature, for example, goes from a minimum of 6.981 to a maximum of 28.11. So this is a brief summary of our dataset, feature by feature. we can calculate a different kind of summary, including, for example, other percentiles. For example, we may want to have a look at the outliers, for example, the 5th percentile and the 95th percentile. We can write df.describe percentile. This is a list, and we have to give the values of the percentiles. For example, we can just take a look at the median, so 0.5, and we are going to get only 0.5, but we can have all these values and another values, for example 0.25, 0.5, 0.75, and for example 0.05 and 0.95. This will give us the 5th percentile and the 95th percentile. Percentiles are very useful because they give us an overview of the shape of the distribution of each feature. They can be used only for numerical variables, and we can use describe to take a look at the categorical variables, for example. We can write include, and the value can be a list with the names of the types of the objects we want to describe. For example, object. In this way, we are including the categorical variables. And this is the result. We have the count of the records that have some value for this variable here, the unique values of this variable, and the value that has the highest frequency, and obviously its frequency. If we take a look at the counts, we see that A is actually the value with the highest frequency, and its frequency is actually 489. So this is a very simple and very used technique for taking a look at our dataset deeply, because calculating these values here, we are trying to understand better the shape of the distribution of each feature. We can calculate these values, mean, standard deviation, minimum and maximum values, and the quartiles, because these are the quartiles. And if we want, we can calculate some custom percentiles, for example, the 5th, the 95th percentile, whichever percentile we want. Finally, we can describe even the categorical variables, including the object type. Some categorical variables have the category data type. So it is useful to call this method with include and using object and category together. In this way, we only have an object column, so this is the only column we are going to get. So this is how the summarization works in pandas in Python, and it is very useful because it gives us some insights. For example, we have different orders of magnitude for the mean values of the columns, and we know that in order to make some models work properly, we will have to transform these columns in order to make them share the same order of magnitude. This is how summarization works, and these are some possible insights we can get. Another very common tool to visualize the main features of a dataset is the histogram. So let's first import our dataset. First of all, let's import pandas. Then we can import our dataset. Then we have to draw the histogram of each feature. We can do this with just one line of code, writing df.hist. Now, the result of this method gives us a grid of histograms. Each histogram refers to one particular variable. As you can see, if we have several variables, this image is very hard to read. So it is useful to make several histograms creating clearer images, for example, drawing a group of histograms at a time. For example, let me focus only on the first 4 columns. We can write df.iloc point hist, and we have the histograms of the first 4 columns. As we can see, these columns are very skewed. This tail here is very long if compared with this tail here, and this is true for each feature. So drawing histograms, we get several informations about the features, about the columns, and the skewness of the columns is a very important information because some models require symmetrical features. So maybe for some models these features must be symmetrized properly. So this is one possible way to draw the histogram of the features. We can manipulate the number of the bins, for example, writing bins equal to 20. We have different histograms now. Obviously, the histograms are made using the values of the features, so we are ignoring the missings of each feature. If we increase the number of the bins, we get a more granular histogram, and we lose a great part of information because we have a lot of noise. If we use a small number of bins, we get too few bins and we lose the information as well. So we can revert back 20, for example, but there are several criteria we can use to draw one possible good histogram for each feature. The criterion I usually use in my exploratory data analysis is called RICE criterion. So we can write the RICE string, and this is an adaptive criterion that tries to select the number of bins according to the number of values of our column. So this is a very nice representation of the histogram. If you don't know how many bins you want, but if you just want a quick overview, you can use the RICE criterion. Otherwise, you can use the standard criterion that is used by the hist method. So this is very useful because we still see some properties of the features, that is, for example, the skewness. But we have seen in the previous lessons that we have a categorical variable. So we would like to see the frequency of the values of this categorical variable. This categorical variable is area error. If we want just the values of just the frequencies of the values, we can write value counts. We can plot an histogram, that is a bar chart of this data here, writing plot kind bar. And this is the result. So the main idea is that the histograms give us a very clear overview of the shape of the distribution of each column. We can draw all the histograms together, but it is pretty noisy. If we don't want all this stuff to appear, we just have to import matplotlib. And we can write plt.show here. So this stuff here disappears. It is useful to draw different bulks of histograms, for example 4 at a time, and we can change the number of the bins if, for example, an histogram is not too clear. But if we don't know the number of the bins to use, we can just leave this argument blank, so Python will give it its default value, or we can use the RICE criterion, which I personally prefer. Then we can draw the histogram of the categorical variables. We can calculate the series that contains the variable. We can use the value counts method and then plot with kind bar. So histograms will give us a very nice overview of the shape of the distribution. And as we can see, several distributions are very skewed. Let's now see a particular kind of plot, that is the box plot. Box plot is a type of plot that helps us understand the shape of the distribution of a variable in a dataset. So let's first import pandas. Then let's import our dataset. Now let's consider for one moment the first column. So if we write the names of the columns, it is mean radius. The plot we are going to draw, it is the box plot, and we can use the box plot method of a pandas data frame. So df mean radius point box plot. Remember that box plot is a method of a pandas data frame, so we have to use the double square brackets here. And this is the result. Let's see how this plot works. This green line here is the median of this column. The upper side of this box here is the third quartile, or the 75th percentile. This lower side here is the first quartile, or the 25th percentile. So half of the points inside this box here. This is the axis related to the values of the variable. And again, this is the median, so the second quartile. Now we see that we have these lines here. How can we draw these lines? We take what is called the interquartile range, that is this width here. So the difference between the third and the first quartiles. This is called IQR, interquartile range. Then, in order to draw this line here, we start from the third quartile, we add the interquartile range multiplied by 1.5, and this is the closest point to this level, the closest point of the points that are less than this level. The same applies here. We take the first quartile, we subtract the interquartile range multiplied by 1.5, and this is the lowest point that is greater than this level. These points here that lie farther from the third quartile are the outliers. So the idea is that in this way we can get a clear idea of the shape of the distribution. We see that we have several points here in a very small range if compared with the whole range of the variable. So this distribution is very tight. It is asymmetrical because the median is here, but we have several points greater than the median value, and we have several outliers that are these points here. Outliers can be both in this part of the chart and in this part here, but in this case the variable has outliers only here. So the idea of box plot is that it gives us a better understanding of how many outliers do we have. So we see that this is called a fat tail, so we have several outliers on one side of the distribution. We don't have outliers here. It is very clear if we draw, for example, the histogram of this variable. You see, these are the outliers. They lie nearly from 22 to plus infinity here. This is the tail. And here we have the majority of the points, and this is why we have the box here. The box contains 50% of the points because we go from the 75th percentile from the 25th percentile. So in this way, box plot gives us a clear idea of the shape of the distribution without using an histogram explicitly. We are not making assumptions on the bindings like in a histogram. These are all levels that are perfectly determined starting from the points. As usual in pandas, we can draw several box plots, for example, for the first two variables. We just have to add the names of the variables in the square brackets here. And we have several box plots. Let's see this other variable here. We see that this variable 2 has outliers, and it is skewed as well, because we have more points in one side than in the other side. Let's, for example, draw the box plot of the first 5 variables. We can use the iLock method. As you can see, we have this variable here that has a very large order of magnitude if compared with these variables here. As you can see, the box plots of these other variables are nearly invisible if compared with this box plot here. And this gives us an information about the order of magnitude of the features. So there is this variable here that has a very high order of magnitude if compared with the orders of magnitude of these other features here. So it has to be handled properly. So box plot is very useful because it gives us a clear understanding of the shape of the distribution. Maybe it can be wide, and it is very important if there are several outliers. Outliers must be handled properly. So let's remember how this plot is built. The central line here is the median. The upper side of the box is the third quartile. The lower side of the box is the first quartile. The height of this box is called interquartile range, IQR. This line here is related to the highest point in our dataset that is lower than the value we obtain taking the third quartile and summing 1.5 times the interquartile range. This line here is related to the point in our dataset that it is the lowest point, that is higher than the first quartile minus 1.5 times the interquartile range. All the points that lie above or below these lines here are the outliers. So we have a clear picture of how many outliers we have. We have outliers only on the right side of the distribution, and it is confirmed by our histogram here. These are the outliers. We have a very tight distribution because we span from 3 to 30, but 50% of the points lie, we can say, from 12 to 16. So this distribution is quite tight, and it is confirmed by the histogram. So the box plot is very useful when we want to have a clear picture of the shape of the distribution of the variables of a dataset. The object we are going to see in this lesson is called pair plot. The pair plot is a plot in which we see the correlation between one variable and another one. So let's first import pandas. And now, for this example, I'm going to use the powerful Seaborn library of Python. It is often called SNS with the alias. Now we can import our dataset. And now we can draw the pair plot. For this example, I'm going to use just the first 5 columns for simplicity. So we can write SNS point pair plot, df, and the result is almost ready. So in the x-axis we find all the 5 features, and we find all the 5 features in the y-axis. So as you can see, mean radius and mean smoothness don't show any particular correlation. You see this is a blob without any particular shape. But if we take a look at the mean perimeter and the mean area, we see a strong correlation. As mean perimeter increases, mean area increases as well. The same applies here with mean radius and mean perimeter, in which we have a very strong linear correlation, and we have a similar correlation here with mean area and mean radius. Obviously, we have a symmetrical situation from the lower diagonal part of this matrix of plots and the upper diagonal part, because we are just switching axes. On the diagonal part, Seaborn draws the histogram of this feature. So this is a very powerful plot because it gives us several information. For example, that these two features here are very correlated, while these two features here or these two features here are not so correlated. This is a shapeless blob, so we don't see any particular trend or any particular figure. We see here or here a very strong trend and a very strong relationship between these features. So the pair plot is very powerful and very easy to use. We can draw a pair plot in this way using just one line of code. It is useful to draw a matrix of pair plot with no more than 5 variables, because if we use several variables, this matrix becomes difficult to see and to read. So if we have several variables, it is useful to draw these pair plots in bulks. So the first 5 columns, the other 5 columns, and so on. And we must take into account that we have to apply all the combinations. So the first column with the 10th column and so on. So this is a very strong and powerful tool to see if there are correlation between the numerical features. Now, we can plot several things with the pair plot. For example, we can plot the pair plot in form of a histogram for each pair of the features. For this example, I'm going to use just the first 100 rows only for simplicity, but we can apply these calculations even to greater dataset. Of course, the larger the dataset, the slower the computation. If we want to see a multivariate histogram instead of a scatter plot, we can use kind hist. In this way, we have a multivariate histogram for each pair of the features. It is very useful when we want to see if there are any accumulation points, for example here or here. Another important visualization can be the kernel density estimation. So kind kernel density estimation. Kernel density estimation gives us an idea of the shape of the distribution without applying the binning that is typical of the histograms. And it is quite a complex algorithm, so it is pretty slow. As you can see, we have a smooth line here and some smooth lines here for the multivariate plots. The diagonal part is always related to the frequency of the values of the feature. So in this case, we are plotting a kernel density estimation. It is a continuous curve that tries to fit the distribution of the feature. In the multivariate approach, we have a multivariate kernel density estimation. Now, since the matrix of this plot is symmetrical, for simplicity, we can draw only one corner of this matrix, discarding the other one because it is exactly symmetrical. We can go back to the usual scatter plot, and if we just want to draw the lower corner, we can write corner equal to true. As we can see, we have lost the first part. We have lost this part here because it is symmetrical with respect to the diagonal part. So I prefer using this visualization here, because if we use this visualization, we can get wrong if we see something here that we may think that is different from here, but these two plots are exactly the same, but they are symmetrical. So if we want to catch the the information without duplicating it, it is very useful to use this approach here with the corner. Now, a very interesting feature of Seaborn is that we can choose the variables to put in the x-axis and in the y-axis. For example, we can use the whole dataset and write x vars, for example, mean radius and mean texture, and y vars is exactly the same, but we add, for example, the mean area. In this way, we are working with the entire dataset, but we are focusing only on these features here. As you can see, we have mean radius and mean texture on the x-axis, and mean radius, mean texture, and mean area on the y-axis. So this is very useful when we want to plot bulks of pair plots in order to avoid the use of a very huge matrix. As we can see, this matrix is no longer diagonal, but when we try to correlate one feature with herself, we still have the histogram. Now, another very interesting feature of Seaborn is that it is able to create colored scatter plots and histograms according to the values of a categorical variable, for example, a target variable of a classification problem. We can write hue, for example, target. As we can see, target is a variable whose values are 0 and 1. For each plot, Seaborn has given a color to each point according to the value of the target variable. This is very useful because we can see a clear correlation. If mean radius is greater than 20, the target is always 0. If it's lower than, I think this is 16, it is 1. So we can see the beginning of a correlation between the features and a possible target variable. The histograms have been replaced by the kernel density estimations made in a conditional way according to the values of the target. So this is the kernel density estimation of the mean radius for all those records that have the target equal to 0, and this is the kernel density estimation of the same features for all those records whose values are 1. So it is very helpful and useful when we want to study the correlations between the features and the relationships between the features and a possible target variable. So this is a very powerful tool. Pair plots are very used, and I think they are very useful when we want to have a multivariate site of our dataset. Of course, pair plot and Seaborn have several arguments more than these ones here, but according to my experience, you are going to work with these setups. So this is what I think is very useful in the everyday job of a data scientist. So let's go back and summarize what we have learned. We have seen a pair scatter plot of each column with the other ones. Of course, each plot is made only on those records in which we have values. The diagonal part of this pair plot matrix is the histogram of each feature. As we can see, these two features, mean radius and mean area, are strongly related with each other, while, for example, these two features here, mean texture and mean area, are not so related because we don't see a clear trend in these features. We can plot an example of multivariate histogram instead of multivariate scatter plots. We can plot the kernel density estimations for a single feature and for couples of features. We can, for example, draw only a corner of this matrix because this matrix is symmetrical, so we don't need all the matrix. We can just draw, for example, the lower corner. And we can choose the features to put in the x-axis and the features to put in the y-axis. Finally, we can give a color to each point according to the value of a categorical variable that might be, for example, a target variable of a classification problem or any other categorical variable we want. In this case, the histograms are replaced with kernel density estimations, and the scatter plots are still scatter plots with the points that have a different color according to the value of this variable here. Remember, for doing this particular transformation, for doing this particular representation, we have to use this argument here. This is the name of the variable we want to use to give each point a color according to a different value. So pair plot is one of the first visualization of a multivariate dataset, and it can give a very huge help to the data scientist because it is a very powerful visualization. We see that here we have some correlated features, and we have several features that are not correlated with each other. And this is a very strong information. If we have a regression problem, we can, for example, take a look at the correlation between each feature and the target variable. If we work with a classification problem just like this one, maybe this approach here with the hue parameter is more useful. So this is how pair plots work in Python using Seaborn, and this is a possible way to read these pair plots. So taking a look at the presence of a relationship, a strong relationship. Remember that when you see blobs like this that have no shape, you are not in front of a relationship. When you see a strong relationship, for example, a line that might not be linear as this one, but might be, for example, this line here, we have a strong relationship. So look for this kind of patterns, straight lines or functional representations, so some kind of shape in these scatter plots. So when you see some kind of blobs, there is no relationship. So this is one possible way to draw pair plots in Python and to read pair plots in an exploratory data analysis. Let's now see how we can visualize the correlation between several columns in our dataset. Correlation is a very important statistical tool because it is able to help us spot the causation. Remember that correlation is not equal to causation, but it can help us spot causation if it is present. So it can really make us figure out which features are useful for predicting a particular target. First of all, let's import pandas. Then let's import Seaborn and matplotlib. Now we can import our dataset. And now we can first define the correlation matrix. Let's create a markdown cell here. Correlation matrix is a matrix, a square matrix. Each element of this matrix is the correlation between two columns of our dataset. The first column is related to the row, and the second column is related to the column of the correlation matrix. Since correlation is symmetrical, if related to numerical features, this matrix is symmetrical as well, and its diagonal elements are all 1. So for calculating the correlation matrix of a pandas data frame, we just write cor. We just use the cor method, and this is the result. This number here, for example, is the correlation between this column and this column. Each element of this matrix is the correlation between the column whose name is the name of the row and the column whose name is the name of the column. As you can see, we have all ones in the diagonal part because obviously each feature is perfectly correlated with herself. The default method for the correlation matrix and for the calculation of the elements of the correlation matrix is the Pearson linear correlation coefficient. But we can use, for example, the Spearman's linear correlation coefficient using method equal to Spearman. And this is the result. It is slightly different. If two variables are very correlated, the absolute value of their correlation coefficient is similar to 1. In this case, for example, mean radius is highly correlated with mean perimeter because their correlation value is 0.99. These other features here have a low correlation because the correlation coefficient is 0.10. When the correlation coefficient is positive, if the value of a variable increases, the value of the other variable increases as well. In this case, we have a negative correlation, so if the value of a variable increases, the value of the other variable decreases. The higher the absolute value of the correlation coefficient, the higher the intensity of the correlation. So this is a very powerful tool to spot the correlation between the features, and if one of these features is the target variable of, for example, a regression problem, this is very useful to see which features are very correlated with the target. But this is a table of numbers. We usually perform graphical analysis because charts and visualization are very useful for making a multivariate analysis. That is why we are going to use what is called the heat map using Seaborn. For this example, let's create a figure that is wider than the standard size. So plt.fig size figure fig size, for example, 12 and 8. Now we want to plot, for example, a heat map of this matrix here. We just have to write SNS.heat of the correlation matrix and then plt.show. Let's see what happens here. This is a heat map. The gradient on the right side gives us a clear overview of the intensity of the correlation. As we can see, the lighter the color, the higher the correlation. So these two variables here, mean radius and mean perimeter, are very correlated, and they are positively correlated because we have a lighter color. Darker color mean a negative correlation. For example, this value here, this feature, mean fractal dimension with the mean radius. So in this way, we have a clear overview of the correlation of the features without taking a look at numbers, but taking a look at a simple chart. Since we want the absolute value of the correlation, because we in first approximation are not interested in the sign of the correlation, we are just interested in the intensity of the correlation, we can create a new heat map using the ABS method. In this way, our gradient goes from 0 to 1, and as we can see, the most correlated features without taking a look at the sign of the correlation are these features here, where the color is lighter. Of course, the diagonal part of the heat map is white because each feature is positively correlated with herself. These features here that are darker are related to absolute values of the correlation coefficient that are similar to 0. So these couple of features are not so correlated with each other. So if we want to take a look at the correlation between couples of features, we can just use this correlation matrix here that gives us a table of numbers. we can change the method, for example, the Spearman correlation coefficient. Remember that the Pearson linear correlation coefficient works with linear correlations. Spearman works with monotonic correlations that might not be linear. But my suggestion is to use a heat map in which we can see graphically the couples of features that are more correlated. And since we want to see the intensity of the correlation, we are not interested in the sign of the correlation, my suggestion is to use the absolute value of each element of the matrix and plot this kind of correlation here. The correlation matrix is very important. It is obviously related to the correlation pair plots we have seen before, but it gives us a clear overview of the most correlated features of our dataset. If one of the columns is a target variable, we see the most correlated features to the target variable. This works better with a target variable that is numerical, so it works with regression problem. But this kind of chart is very useful to spot those features that are very correlated with each other, and it is called collinearity. Collinearity is a great problem for several models, not for all models, fortunately, because having features that are very correlated with each other can create problems in the training phase of our model, may not increase the information carried by the features, so we may remove one feature. It is not always true, but sometimes it is true. So removing a useless feature may be useful to reduce the dimensionality of our problem, and it may be a problem when we work, for example, with unsupervised machine learning, in which we don't have a target variable to analyze the correlation with, and we need to reduce the dimensionality. Using uncorrelated features may be a good choice for unsupervised problems. So this is a clear chart of what happens when it comes to talking about correlation. The idea is that we want our features to have low values for the correlation coefficient. So according to this gradient, we would like this chart to be as dark as possible. As we can see, it is pretty dark, but we still have features that are correlated with each other. These are the most correlated features, and these are less correlated, but they are still correlated. So this is how we study the correlation between the features. Remember, the higher the absolute value of the correlation coefficient we want to use, either Pearson or Spearman, the higher the correlation, and the higher the probability that one of the two features that are correlated with each other may be removed, because it may not increase the predictive power of the dataset. Let's now see a very powerful method to assess the predictive power of a numerical variable against a categorical target. I'm talking about the stacked histograms. So let's first import pandas. Then let's import Seaborn. And let's import our dataset. Now let's see the columns of our dataset, and let's consider this column here, for example, mean radius. We want to see how mean radius is able to predict the value of the target variable. That is a categorical target with values 0 and 1, so it is a binary classification target. The idea of the predictive power of a feature is that, knowing the value of the feature, are we able to predict the value of the target variable with high accuracy? So the idea is to create an histogram of, for example, this value here against the values 0 and 1 of the target variable. Let's draw this histogram. We can use Seaborn, so SNS.hist.plot. We pass the entire data frame. Then we write x equal to the name of the column, mean radius. Then hue equal to target, that is the value, that is the target variable, and multiple stack. This is what happens. For each bin, the height of the bar that represents the count of the records in the dataset that fall in this bin has been split according to the values of the target variable. So as you can see in this bin here, we have more ones than zeros for the target variable. In this bin here, we have only zeros because we only have this color here, this blue here. So the idea of this histogram is that we can find those intervals of the feature in which we have a great part of records related to one value of the target variable. As you can see, for this interval here from 0 to 15, all the bars are mostly orange. So we have a very great part of ones and a very small part of zeros. As you can see, the blue bars are not so tall if compared with the orange bars. For values from 15 to plus infinity, we have a very great part of zeros and less ones. So as we can see, if we, for example, select this bar here, we have almost 100% probability of having 0. If we select this bar here, we have almost 100% probability of having 1. There is still a low probability of having 0, but is very low if compared with the probability of having 1. So we can say that this variable is highly predictive, because if we pick one value of this variable, for values less than 15, we can say that we have 1 for the target variable. For values greater than 15, we can say we have 0. How can we decide if a variable is predictive or not? If we can find intervals in which we have one value of the target variable that has a very high frequency and the other values have a very low frequency. So there is one value that takes most of the frequency. In this way, picking a value, we have a high probability that we are right. We can find this cutoff here in which the behavior of the target variable switches. As you can see in this bar here, we have a very great part of ones, but in this bar here, the situation is the opposite. We have a very great part of zeros. So we can easily find a cutoff at which the target variable switches its behavior and the other value becomes more frequent than in the nearest interval. So this is the idea. When we have a stacked histogram in which each bar has a majority class for the target variable whose frequency is very, very high if compared with the frequency of the other classes, we can say that the variable is highly predictive. This behavior must be checked for each bar. It is not always true that a feature shows this behavior for each bar, but if we have a great part of bars in which one class is the majority class and its frequency is very high if compared with the other classes, we can say that the variable is highly predictive. Let's change the variable. For example, let's consider this variable here, worst concavity. Again, x is the variable we are putting in the x-axis. Target is the target variable whose values change the color of the bars. So in this case here, we see that these bars are very predictive because we have a majority class that is 1 and has a very high frequency if compared with the frequency of the zeros. These bars here are not so predictive because the frequency of 0 and frequency of 1 are very comparable. In this bar here we almost have 50% zeros and 50% ones. but starting from this point, zeros start to be more frequent than 1. So this variable is highly predictive, although we have an interval in which we have a mixed situation. Let's change, for example, another column, the worst perimeter, for example. The concept is the same, because for this interval here, we have a great part of 1 for each bar. If we pick a value here, we have a strong probability of having 1. From this point to plus infinity, we have a high probability of having 0 for each bar. If we pick this bar here, we have a high probability of having 0, although it is very similar to 1. But from this point here, we have a very strong probability of having 0 for each bar. Remember, this concept must be applied for each bar. If we want to plot all the columns together, we must use a for cycle. So first of all, let's consider only the numerical columns. So df point select the types, exclude object. This will give us a data frame with only numerical variables, but the target variable is one of these numerical variables. Of course, we don't want to plot the target variable as a variable to be put in the x-axis, so we can drop it. And these are the names of the columns. The numerical columns. So we want to plot one histogram for each column. We can create a plot grid made by a subplot. So we have to import matplotlib first. And then we can write figure axis plt point subplots. Let's say we want one plot for each row. So the number of the rows is the length of the columns array. The number of the columns is 1, and the size, for example, might be for the x-axis 5, and for the y-axis 5 multiplied by the length of the columns. Then we can write for I in range len columns. The column name of the ith column is columns I, and we can plot the hist plot. This is column name, and we can pass the matplotlib axis, that is a axis with the index I. This is the result. It takes some seconds because we have several features. But we have a grid with all the plots, all the histograms, one for each feature. As you can see, these features are very predictive because for each bar we can identify one majority class with a very high frequency. This is true here, but is less true, as you can see, because here we have quite a high value of the frequency of the minority class, although we have a majority class. It's very true here. Each bar has almost one color. This is true here, but for this bar here it is not a problem. Here we have this interval that is very predictive, this interval from here to plus infinity that is very predictive, but this range here is not so predictive because we have a majority class that has almost the same frequency of the minority class. As you can see, the colors here are very similar in the height of the bar. And so on. This is the way we can see if a numerical variable is predictive with respect to a categorical target. Remember, we want to calculate with a high precision the value of the categorical target according to the value of the numerical target. We can see the predictive power of the numerical target, for example, using these stacked histograms here. How can we see it? If each bar has a strong frequency for only one class of the categorical variable. This approach can be easily applied even to multi-class classification problems in which we have a target variable that has several classes. For this example, I've used a binary classification problem. So each bar must have a majority class with a very high frequency if compared with the frequency of the other classes. In this way, we can say, for example, that a value that falls in this interval here of this bar gives with a very high probability a target variable whose value is 1. This is the purpose of the stacked histograms. These are very useful when you work with a classification problem and you have numerical features. So remember, for each bar, see if the majority class has a very high frequency if compared with the frequencies of the other classes. If so, we can predict the value of the target variable with a very high accuracy. It is very useful when we see this behavior in sub-intervals in the domain of the feature. For example, from 0 to 15, in this case, we have one behavior. We can predict 1 easily. And from 15 to plus infinity, we can predict 0 easily. So this is how stacked histograms work for a binary classification problem. They can work even with multi-class classification problems. In this lesson, we are going to see a very powerful library that allows us to perform exploratory data analysis writing just a few lines of code. This library is SweetWiz. So first of all, let's import it. Then we can import pandas. And then we can import our dataset. Now we can analyze this dataset using SweetWiz. First of all, we have to create an object that contains all the calculations that are made by SweetWiz. This library performs all the exploratory data analysis calculations in advance, like, for example, the summarization or the percentage of the missings and the percentage of the target variable according to the bins of an input feature. All this data is stored inside a particular object. Then this data is rendered using some graphical tools. So first of all, we have to create this object. We can call this object report, and we can create it in this way: SweetWiz point analyze. The first argument is the data frame. Then we can write target fit and the name of the target variable. We can execute this code and the progress bar will show us the progress of the calculation. SweetWiz is performing all the calculation for each feature. It may take a while if your dataset is quite huge. Now the calculation have finished, and then we can plot them using, for example, this code: report point show HTML layout vertical. If we work with Jupyter in our laptop, another window will appear, but if we work with, for example, other tools like Google Collaboratory or other kinds of online notebooks, we will have to open this window manually. So we can execute this cell and this window appears. So this is a common representation of data using SweetWiz. First of all, we can take a look at the shape of our data frame, how many rows it has, how heavy it is in RAM, how many features this data frame has, and so on. Then we see a practical histogram of the target variable, how many ones and zeros we have. And if we click here, we get a larger view and the correlation with the features. This is the categorical association with the categorical variables, and these are the features, the categorical features that give information to the target variable. Of course, we have only one categorical variable in this dataset, so we are only going to see one name here. Then we have the correlation with the numerical features, sorted from the most correlated one to the less correlated feature. And as we can see, this is the most correlated feature to this target variable. Here we have an histogram with the top categories of the values of the categorical target variable. How many missings we have? In this case, we don't have any missings, and the distinct values. In this case, 2, because we have only 0 and 1. If we go on analyzing this report, we get an analysis for each feature. For example, for mean radius, we have this number of values. These records show a missing. These are the distinct values, and these are the zeros. Then we have the summary statistics, the maximum, the 95th percentile, the quantiles, the average value, the median, and so on, the kurtosis, skewness, and the sum. Then we have this histogram here, in which for each bin we have the percentage of ones in the target variable. This is very similar to the stacked histogram we have seen so far. This line represents the percentage of ones of the target variable. So this bar here is related to an interval in which we have almost 100% of ones. As we can see, the percentage decreases as the value of the feature increases. If we click on this line, we get a larger view of this histogram. We get the numerical association with the other features, with the other numerical features, and the correlation with the categorical variables that are the target variable and the area error. Then we have other statistics, like for example the most frequent values, the smallest values, and the largest values. So we have everything in just a quick site. We can change the number of the bins of the histogram, for example. I suggest using auto. And this is made for all the features. Each feature is calculated in this way. We have the overall summary statistics, the missing statistics, this histogram in which we see the correlation with the categorical target, and the numerical associations that are the correlation coefficients, the linear correlation coefficients between each feature and this feature we are analyzing. So it's very powerful from this point of view. This is done for each feature, as we can see, but we have another interesting feature, that is the association heat map. The square and the rectangles represent the intensity of the correlation between a feature and a categorical feature. In this case, the target is a categorical feature, so we only have squares. The circles represent the numerical correlation between one feature and another feature. They go from -1 to 1. As we can see, we have these features here that are very correlated with each other. And the target is very correlated with these features here. For example, the wider the shape, the higher the intensity of the correlation. And we have a color gradient here. So it is very similar to a correlation heat map we have seen so far, and it is very powerful because it gives us a clear overview of the correlations, even when we talk about categorical features. So SweetVis is very powerful for this kind of quick analysis. It gives us a very quick overview of the features, the correlation with the target, and the correlation between each feature and the other features. Now we can see Another very useful way to represent this analysis, that is the show notebook method. If we use the show notebook method, we have the whole analysis inside a cell of our notebook. My suggestion is to use this code here because it will open a new page of our browser. It creates a new file, an HTML file that we can see, we can use, and we can interact with. Another powerful use of SweetWiz is its capability of comparing two datasets with each other. We can create a new object, report2, that is SweetWiz point compare. We must write a list. The first object of this list is the first dataset we want to compare. Let's consider, for example, the first 50 rows of our dataset. So df.head 50. Then we have a string that is the name, for example, dataset1. Then we have another list that contains the other dataset, for example, the last 50 lines, df.tail 50, and a string dataset2. Finally, the target variable, target fit target. Then we can write report2.show HTML layout vertical, and we have all the calculations that compare these two datasets with each other. Of course, we have two datasets, and SweetWiz will take a bit longer to perform all the calculations, but as we can see, since these datasets are not so large, SweetWiz is pretty fast. Now a new window will appear, and this is the result. As we can see, we have all the analysis we have seen so far duplicated for the first and the second datasets. So the target histogram is split among the two datasets. Each analysis is split among the two datasets. The maximum value, the 95th percentile, and so on. The first dataset is blue, the second dataset is orange. So we have all the same data as before, but they are split between the first and the second dataset. So it is a very common approach when we when we want to compare two datasets, or we want to see if the test dataset in a machine learning project is statistically similar to the training dataset. In order to train a model in a useful dataset similar to the dataset we are going to test it on. So these are two main possible uses of SweetWiz. We have the exploratory data analysis of one single dataset with respect to a target variable, and we have all the summary statistics and the correlations between the features and the target in the form of this kind of line here. Each point of the line is the fraction of ones in the target variable that are related to this interval here of the feature. Then we have the associations plot that are this particular heat map here. The larger the size of the shape, the higher the intensity of the correlation. The squares are the correlation between a categorical variable and another variable. The circles are the correlations between two numerical variables. Then we can use SweetWiz to compare two datasets with each other. So it's a very useful tool because we can do several things with just one line of code. If we write just show HTML, the result is this one. If I click here, I don't get any particular result because I have to scroll on the right part of the page in order to get the results. I think this is not so useful and handy when it comes to analyzing data in a quick exploratory data analysis. So I prefer using the vertical layout That is the layout I have used before. So this is one possible way to use SweetWiz library to perform a simple and quick exploratory data analysis. Let's now see another library that is very useful for performing exploratory data analysis using a low amount of lines of code. This is similar to SweetWiz library, and it is called pandas profiling. So first of all, let's import pandas and let's import our dataset. Then we have to import the profile report object of the library pandas profiling. So we can go back to the import section of our notebook, from pandas profiling, import profile report. This is the object we are going to use. Then, just like SweetWiz, we have to create a report object that is an instance of this object here. The first argument is the data frame we want to work with. For this example, since automated exploratory data analysis involves complex calculations, we are going to work only with the first 5 columns of our data frame. But of course, we need to work with all the columns if we want to use a complete exploratory data analysis. So we can write df.iloc 0.5. This creates the object but doesn't perform the calculations. If we want to see the results of the exploratory data analysis, we can simply write report point to notebook iframe. The calculations are made. We can see the progress bar, and in a few seconds we can see the result. As you can see, we have an overview with the main details of our data frame, the number of the variables, the number of the observations, the missing cells, the percentage of missing cells, and so on, the duplicate rows, and so on. Then we have the single variables. In this case, pandas profiling gives us some information about the correlation. For example, here we have a warning. This variable has a high correlation with 2 fields, mean perimeter and mean area. And about the missings, we have a pretty high percentage of missings, 15.3%. We have all the main statistics about the feature. And if we click on toggle details, we can see a more detailed report of the statistics, the minimum, the 5th percentile, the quantiles, the quartiles, the range, the interquartile range, and so on. Some descriptive statistics, some variance, standard deviation, and so on. The histogram, some of the most common values with their frequency, and the extreme values, the minimum find values and the maximum find values. This is true for each single feature. We have a warning about the correlation, a warning about the missings, some of the most important metrics, and if we click on toggle details, we have other important metrics here. But we have some other interesting things in our report. For example, the interactions. If we select one feature and another feature, we get the scatter plot and the pair plot we have seen so far. So these 2 features are not so correlated with each other, but if we click here, we see that these 2 features show a very strong linear correlation in this case. And we can plot this representation for each couple of features we want. Of course, we cannot correlate a feature with itself. Then we have a report about the correlation. We have 4 correlation coefficients here, and this is the heat map that shows the correlation between each feature and the other features according to the selected correlation coefficient. we have the possibility to show the description of the correlation coefficients that are used, if we don't remember them from statistics. And finally, we have a report about the missing values with the count of the missing values for each feature, a matrix if there are some patterns about the combination of missing values among the features, a heat map that gives us how strongly the presence or absence of one variable affects the presence of another. So if there is some correlation about the missing values, the missing cells. And finally, a representation in this way with a simple dendrogram. Finally, we have a sample with the first rows and the last rows. So this is a very useful library when we want to have a quick sight about our data frame. We can reach all the sections here using this bar: interactions, correlation, missing values, and samples. But there are some other possible uses of this library. For example, we can create an HTML file of our report. We can write report point to file and the name of the file, report.html, for example. In this case, the report is exported in an HTML file, and we can take a look at this file. If we want to export the file and move directly to this file, we can use silent equal to false. In this case, the report has been created and we are automatically redirected to our report that is the same report we have seen before, but in a larger view as a unique HTML file. So this is very useful when we want to give a report to some other people. We just have to create this file and we can give this file to whoever we want. Now, since the calculations of all the metrics and the scatter plots and the correlation can be quite difficult to perform and computationally expensive, we can create all these statistics avoiding the multivariate statistics, using only the univariate statistics, so the histograms, the basic statistics, and telling pandas profiling not to calculate the multivariate part, so not to calculate the correlations and the scatter plots. In order to do so, we can create another object here. Avoid the calculation of multivariate statistics. We just have to use this argument here, minimal true. Then we can show the report. Report point to notebook iframe. The calculation is faster, as you can see, but we lose all the computationally expensive part that are the correlations and the interactions. We just have the univariate statistics here, the statistics related to each column individually. So the histogram, the common values, and so on. This is very useful when we are not interested in the interaction part or the correlation part. We just want to take a quick look at the univariate statistics of our data frame. So this is a very useful and commonly used library. Of course, there are several other options we have to we can set, but for a general purpose work of a data scientist, we can just use these simple functions we have seen so far. So if we don't set anything, we calculate the interactions and the correlations and so on, and all the univariate and multivariate statistics. We have the correlations with several types of correlation coefficients, and if we want, we have the scientific explanation about each correlation coefficient. We have our heat map, and we have, of course, the interactions. All the interactions we make with Seaborn, for example, can be visualized here.